Hi folks, I just want to take a quick look at the connection between the slope, the direction vector, and the normal vector of a line in two dimensions. Okay, so let's say you've got some line here, and say the direction vector of this line is, let's say, 3, 2. Okay, so pretty easy to see the connection between the direction vector and the slope, because this direction vector is parallel to the line. So let's say I were to move it, as I can with any vector, and say I move this vector onto the line. Okay, so here's my vector m, and I know that the slope is just found by, calculating rise over run between any 2 points. So here, if I think about this vector as defining my rise over run, I see that my run is just the x value of the vector, in this case 3, and the rise is just the y component of this vector 3, 2. Okay, and so the slope, okay, notice here the arrow on top, direction vector, no arrow represents the slope, is just the y value of the direction vector over the x value of the direction vector. Okay, so if you have the direction vector, the slope is easily found by y over x. Okay, or if I'm given the slope, I just take the numerator, which would be the y value of my direction vector, and the denominator, which would be the x value of the direction vector. Okay, so there's a connection here. Another connection I want to make too is if we're working with the Cartesian equation of the line, I'm interested in a normal vector. But we know the relationship between the slope of a line and a line perpendicular to it. It's the negative reciprocal. Okay, so the slope that is perpendicular to the given one would just be the negative reciprocal, so negative 3 over 2. Okay, now if we take a look at this here, you can create the slope for that normal vector. Okay, so this 2 now becomes negative 2, and this 3, which was our run, now becomes our rise. And we realize that this vector here, this normal vector to the line, is just given by negative 2, 3. Okay? Of course, we could have also taken the normal vector in the other direction to negative 3. That would have also worked. Call that n1 as a normal vector. But what I want to look at here is the relationship between the direction vector and the normal vector. And here we see that all you have to do is switch around the x and y components, okay, and then change the sign of one of them. Okay, so in this case here, the direction vector 3, 2 became the normal vector negative 2, 3, or the normal vector 2, negative 3. Okay, so let's just take a look at the way we would use this in examples. So let's say let's just make something up. Say we're find the Cartesian equation of r equals, let's say, 5, 7 plus t times 5, negative 3. Okay. So here we have the vector equation of a line, and say they want us to find the Cartesian equation, so we need a normal vector in order to do that. Okay, well here I look at my direction vector, which is just the vector that multiplies our parameter t. Okay, so that's 5, negative 3. So from here, instead of having to, do some work to determine a vector that's perpendicular to it, I can say right off the bat the normal vector would be, or a normal vector, because there's many. Okay, we just switch the components, and here this negative, well, if we're taking the negative of it, will now become positive. So 3, 5 would be a normal vector, or, if you wanted to, I don't know why you'd want to, but if you did, negative 3, negative 5 would also work. Okay. Alternatively, let's say they ask you to find the parametric equation of 5x plus 7y equals 9. Okay, so in other words, something that's given in Cartesian form. Well, I know that in Cartesian form, the coefficients of x and y represent my normal vector. So normal vector here would be 5, 7. And if I'm looking for the parametric equation, I know that I need a direction vector. So here, in order to find my direction vector, I would just flip around x and y and make one of them negative. So I have one option as 7, negative 5, or another option would be negative 7, positive 5. Okay, so just a little trick you can use. Now, of course, this only works in 2 dimensions. As in 3 dimensions, the only equation we have for a line is the vector slash parametric slash symmetric equation. Okay, that's it for now. Hope it helps.